Today we'll be discussing CSEC physics, specifically resistance and Ohm's law. I'm Paul Bender. Okay, today our topic will be resistance and Ohm's law. Well, some things I would want us to learn today. By the end of this lesson, you should be able to explain electrical resistance. You should be able to explain electrical resistance, state the relationship between electric current and potential difference, state the relationship between electric current and resistance, and differentiate between the effect of series and parallel arrangements of resistors on current. Now, current electricity is a big part of our lives. The lights, the radio, the television, the cell phones, almost every device that we use, it uses current electricity. By now you would have gone through what is static electricity, and now so we look at what is current electricity. All right. Electric current is defined as the quantity of charge that flows past a point, all right, in a given time. And so we have in this little demonstration here, these are electric charges flowing in this direction. It's repeating itself, but what we see, this is the point at over which the electric charge is flowing. All right? So these charges are flowing. Okay? And so we have a number of them, and we see about 5 of them passing this point in a unit time. All right? But these are just charges that are flowing unimpeded. But in a real situation, all right, these are called lattice atoms, and these electrons, when they go, so these electrons flow, but some of them, they bounce up with the lattice atoms, and not as many of them flow past that particular point. So right now, as we see, as this is repeated, only 2 electrons flow past the point because the others are colliding with the lattice atoms, all right? And so this phenomenon of the electrons, the number of electrons flowing past a particular point, being reduced because of collisions with the lattice atoms, is called resistance. That is what resistance is all about, all right? So the phenomenon that causes the reduction in the electric current is called electrical resistance, because you remember, electric current is the number of charged particles flowing past a point. If you reduce the number of particles, then you would have reduced the electric current. All right? So so what is it that makes charge flow inside of a conductor? You put a conductor. If you connect a circuit, then if you don't connect the battery, then nothing will happen. If you don't plug in your television, it wouldn't work because it doesn't have any what you call voltage or potential difference. So when your charge begins to flow from one point to another in a conductor, when a potential difference is applied across the 2 points. So what is a potential difference? For instance, if I hold this battery or anything like this battery, and I drop it, it will fall, right? It falls into my hand. Now the battery acquires motion because we move it from a high gravitational potential to a lower gravitational potential. There is a difference in potential. High gravitational potential, low gravitational potential. So the battery falls through that potential difference. There is a high to low. In the same way, in a circuit, we have the positive is taken as high and the negative is taken as low. And we have what is called a conventional current, which flows from high to low. But actually, in the conductor, it is negative charges that move in this direction. If we don't have the potential difference, there will be no current flowing. So it is because of the potential difference that current flows. So far, we have looked at electric current, we have looked at resistance, and we have looked at potential difference. And as we said, in the conductor, there is a resistance, and the potential difference causes the charged particles to flow, which produces the current. All right, so we are going to, so in summary, potential difference V, we use the symbol capital V for potential difference, causes electric current I to flow in a conductor. Electrical resistance R of the conductor restricts the flow of the current. So we have three things. We have potential difference, we have resistance, and we have current. And they are interrelated. Okay, and we will look at how they are interrelated, and we'll do just a short demonstration. Okay, so I have here a pair of cells, and this will provide my potential difference. I have here a measuring device, which is an ammeter, which will tell me what the current that is flowing will be. I have here a circuit board with some resistors, and we will look what resistors are a little later. All right, and so the first thing we will look to is the relationship between potential difference and current. So what I will do, here I have these two batteries add up to 3 volts. So I'm going to put 3 volts of potential difference, and I'm going to read the current across a particular part. All right, that's flowing through. So I have about 0.2 amperes of current, right, with the 3 volts. Now I'm going to change that to 9 volts. I'm going to change that to 9 volts, and let's see what happens here. I'll put on a 9-volt battery, and let's see what happens here. So 9 volts. Okay, so 9 volts, let's see what happens here. So we now have 0.50. Remember with the 3 volts, we had 0.20 amperes of current. With the 9 volts, we now have 0.48 amperes of current. So we see as we increase the potential difference, what happens to the current that is flowing. So how does potential difference and resistance affect current? So the first thing, when the potential difference across the current conductors increase, what happens to the current through the conductor? Does it increase? Is it unchanged? Or does it decrease? So the potential difference across the conductor was increased from 3 volts, and we got 0.2 amperes. And when we put 9 volts, we got 0.48 amperes. And so we see that when that happens, it increases. So potential difference increases the current through the conductor once the conductor remains the same. All right. So the next thing we will look at is how does resistance affect potential difference, okay? So right now, I have the 9 volt. Let me move this one. Right now, I have the 9 volt, and that is connected across one resistor, okay? The 9 volts is connected across one resistor. What I'm going to do, I'm going to connect the 9 volts across 2 resistors, and let's see what happens. About 0.46, it's going down a little bit. I'm going to put it across 2 resistors, and it has dropped to 0.28, okay? Across one resistor, then the potential difference is across one resistor, it's about 0.47, 0.48. When I put it across two resistors, it's 0.28. So when I increase the resistance, because I move from one resistor to two resistors, when I increase the resistance, the current decreases. All right, so let's see what it says. It says when the resistance of the conductor is increased, what happens to the current through the conductor? If we go, we said it decreases. So we have a relationship. Potential difference is increased, current is increased. Resistance is increased, current is decreased. So what we're going to do is to establish a relationship amongst R, V, and I, okay, which are, all right, from the results of the demonstration, we can write that the current is proportional to the voltage. Increased voltage, increased current. That's a direct proportionality. We can also write that the current is inversely proportional to R. Remember, when we increased the resistance, the current went down. So there's an inverse relationship. Increase R, current will decrease. Okay, you decrease R, current will increase. And so there's an inverse proportional relationship. We can now combine these two proportionalities. We combine them, and we will get that current is proportional to potential difference divided by resistance, okay? Now, I don't know if you remember force and mass and acceleration, because we said it's kind of similar in the way it is done, because remember we said that acceleration was directly proportional to force, and acceleration is inversely proportional to mass, and that is how we came about our relationship F is equal to ma, because we combine those proportionalities, but when we use everything in SI units, the constant of the proportionality K is equal to 1. And so if all I, V, and R are in SI units, then K is 1, and we can write that I is equal V over R. And that comes from continuous, every time we use circuits, we find that this is true. And so as a result of that, we come up with this equation, I equal V over R. And this equation, relationship, I equal V over R, or we write it in a more familiar form, V is equal to IR, is called Ohm's law, and it is perhaps the fundamental law of current electricity. It's very fundamental. It is used in all instances. It is a law that is there because it repeatedly always prominent in current electricity and resistance and resistances. So this is Ohm's law, this fundamental. Potential difference is equal to the current throughout the conductor times the resistance of the conductor. Okay? And we can use this law in many ways, and we will see how we can use it. All right. So the next thing we're going to look at are what are resistors. All right, I mentioned resistors here. These little things are called resistors. So what are resistors? Resistors are conductors with known electrical resistances, right? Remember we said that when you have a conductor, because of the lattice atoms, they cause the flow of current to be reduced, okay? So they are used in electrical circuits to decrease or increase the current that would flow in particular branches of circuits. Now I'm sure you must be a little querulous about, we said that resistances cause the current to reduce, but yet still I'm saying that resistors can be used to decrease or increase current that would flow in particular branches of the circuit, okay? Remember we said that if you have a resistance, the current is reduced, but yet still this statement is saying decrease or increase. And so let's look and see how that happens. Resistors can be arranged in two basic configurations in a circuit. They are a series arrangement or a parallel arrangement. And it is as a result of these configurations that we can get the decrease or the increase in the current with your resistors. All right? Okay. This is a demonstration. We will look at the effect of series and parallel arrangements of resistors on electric currents. All right? So here's a little demonstration I will do again. Okay. If you look here, we have these two resistors, this one and this one. They are in series arrangement. All right? And then on this part here, we have two resistors in a parallel arrangement and three resistors in a parallel arrangement. So we have two resistors in series, two in parallel, and three in parallel. And we will look on the effect of these parallel and series arrangements on current. Okay, we have our, okay, so we'll be using the 9-volt battery. Okay, so the first one, I will look at one resistor, okay? I will look at one resistor, and we did this already. So when we put in one resistor, we get a current of 0.42 amperes. So I will add another resistor in series, and when I add this resistor in series, I get 0.26 volts, right? So as I increase the number of resistors in series, my current begins to decrease. Okay, as I increase the number of resistors in series, my current begins to decrease. Now, I will now move to putting bring the two parallel resistors. So I'll start with two resistors in parallel, okay? You remember for one resistor, we had a current of about 0.47 amperes. Now we'll put two resistors in parallel, and I put two resistors in parallel. What has happened? We are now at 0.55, all right? I have two resistors in parallel, so I'm now at 0.55. I will now put three resistors in parallel, and let's see what happens. We're now at 0.62. What we see as we increase the number of resistors in the parallel arrangement, our current is actually increasing. This is for two resistors in parallel. Our current is 0.53. And this is for a single resistor. Our current is 0.37, all right? So we see that we move from one resistor to two in parallel to three in parallel. The current increases. And so as we move from one resistor to two resistors in series, the current is decreasing. So hence my statement, all right? How do the resistors affect the current? When the number of identical resistors in a series arrangement is increased, the current decreases. So let's look at that. It decreases, all right? Then, when the number of identical resistors in a parallel arrangement is increased, the current in the circuit increases. So when we put more in parallel, we get less current, okay? And when we put more in series, when we put more in parallel, we get greater current. When we put more in series, we get less current. So when we want to apply these resistor configurations in a circuit, we can use them, as I said before, either to increase the current in that part of the circuit or to decrease the current in that part of the circuit. Okay, because that's how the configurations work. But the resistor by itself, a resistor by itself serves to reduce the current, because we said as these charged particles flow through the conductor, they encounter collisions with the lattice atoms. But how we configure resistors, we can use them to increase or decrease the current in a part of a circuit, right? So, were the objectives met? Let's see what the objectives are. We were asked to explain electrical resistance. I think we did that when we explained electrical resistance. We talked about electrical resistances when the charged particles, they collide with the lattice atoms and so on, right? That's electrical resistance. State the relationship between electric current and potential difference. Let me say, I think we did that, because remember we said that electric current is directly proportional to potential difference, okay? And then state the relationship between electric current and resistance. I think we did that because we said they were inversely proportional. Okay, the electric current was if we increase resistance, current went down, and so on. They were inversely. And differentiate between the effect of series and parallel arrangement of resistors on current. I think we did that because we saw that if you increase the number of resistors in series, the current reduced, and if you increase the number of resistors in parallel, the current increased. All right, we saw that as well. So let's look some questions. All right, some questions for you, and maybe you can try to answer them as well. It said, it is required to reduce the current in a circuit to 2/3 its value. By what factor must the resistance in the circuit be increased? The potential difference is unchanged. We want to require to reduce the current in a circuit to 2/3 its value. All right? So what we want is, what we know is that current is proportional to potential difference, all right? And we know that current is inversely proportional to resistance. We know those two, right? So we want to we're starting with some current, and we want to know by what factor we must increase R so that this current now becomes 2/3 of its value, all right? Okay, so we want a new current. 2/3 I must be proportional to some 1 over some new resistance. Let's call that new resistance R prime, okay? And so what we can do, all right, is to change around this equation, and let's see what we will get. We will get R prime is proportional to 3/2 times I. All right? 3/2 times I. Sorry. 3/2 times 1/I. You can do the algebra. It's just if you had, just as though you had an equal sign, you can cross multiply with the 3, you can cross multiply with the 2, and cross multiply and so on, and you will get this equation. But what we know that 1/I is proportional to R, all right? So R prime must be proportional to 3/2 R. So we must increase R by 1.5 times in order to be able to reduce our current by 2/3. So if we want to reduce our current by 2/3, we must increase our resistance by 3/2. Inverse. It's an inverse relationship, all right? That stands to reason. If you have an inverse relationship, you want to decrease your current by 2/3, then you must increase your resistance by 3/2. Inverse. One is the inverse of the other, all right? So that stands to reason. Okay. So what we see is that we can control how much current we have in any part of a circuit or in any circuit simply by varying the resistance. All right, and we can vary the resistance by any particular amount so that we can control how much current we have within any part of a circuit. And that is very important. Here we see how the importance of Ohm's law is. All right. Here's another question. Is it possible for any number of identical resistors in series to have the same effect on a current as any number of identical resistors in parallel? Is it possible? Remember, in the series arrangement, the more resistors we add is the less current we have. For parallel arrangements, the more resistors we add is the greater the current. So there is no possibility that I can string a number of resistors in series. So here are resistors in series. There is no way, because the more I add, and these are just symbols for resistors and how we put them in parallel and series, and we will look at that at some point. All right. There is no way, because the more of these I add, the less the current becomes. The greater the current becomes. The more of these I add, the less the current becomes. So there is no possibility for me to have identical resistors to have the same effect on a current, because one increases it and one decreases it. Okay? And so we must, if we are going to use this technique in order to increase or decrease current, we must either or. There is no possibility of using one to replace the other. If we want to reduce the current, we add more resistors in series. If we want to increase the current, we add more resistors in parallel. Okay. And then we have, the illustration shows a switch for controlling the speed of a fan. At each number, the switch connects that number of resistors to the circuit with the fan motor. So when you switch to 1, it is connecting 1 resistor. All right? The speed of the fan increases from 1 to 3. So as you click to 1, it goes to a certain speed. When you click to 2, the speed increases. And when you click to 3, the speed is going even faster. I mean, we all have fans, right? Explain whether the resistors that are connected to the fan motor circuit would be A, in series arrangement, or B, in parallel arrangement. And we have a constant voltage. It's plugged into the wall, so the voltage is constant. So as I switch here, I connect one resistor to the fan motor so that there's a certain amount of current going through the fan motor. As I click here, 2 resistors are now connected to the fan motor. So a different current is now flowing through the fan motor. And when I click to 3 resistors are now connected to the fan motor. So there's a different current once again that is connected to the fan motor. All right? Now, if the fan is to increase in speed, it means that the current through the motor must be increasing. Okay? If it is increasing in speed, the current through the fan motor must be increasing. So, how must these resistors be placed if when I click from 1 to 2, the current increases. If the resistors are placed in series, when I click from 1 to 2, then the current would be reduced and the fan will go slower. Because remember, we said that when you increase the number of resistors in series, the resistance increases and the current drops. So if I click from 1 to 2 and the resistors are in parallel arrangement, the two resistors are in parallel, the current increases. We saw that in our demonstrations. If the current increases, the fan will begin to spin faster. When I click from 2 to 3 now, if I have those three resistors in series, then the current will reduce even more. So I will have to put them in a parallel arrangement so that when I click to 3, I now have 3 resistors in series, in parallel, and as a result of that, the current through the circuit will increase and the fan motor will spin faster. All right? So here we see, so as we go, we click from 1 resistor, 2 in parallel, 3 in parallel. Current increases each time, fan motor spins faster. All right? Now, what we've gone through is just what you would call the concept of using Ohm's law and the relationship between current and resistance and potential difference. Okay? If you notice, we didn't do many calculations also, but it's just to get you to understand that this Ohm's law relationship and how resistors are used is so very important in almost all electrical, well, not almost, in all electrical devices that we use. When you open electrical devices, you will see all of these little things inside of it and some other stuff, capacitors and inductors and a number of different things in it. But those things help and produce that current voltage resistance relationship. And it is very important and it's a fundamental part of how many of our devices, electrical devices and so on, are built. And so I hope you got an understanding, a conceptual understanding of how we use resistors in series and in parallel to control currents in various parts of our circuit.